When you learn acid-base chemistry, you're taught about acids and bases. And typically, you start off by considering the reactions of acids in water or bases in water. And an acid is a proton donor to water, and a base is a proton acceptor. Well, what do we really mean by that? What is happening in a reaction? Let's look at the reaction of HCl, that's hydrochloric acid, and water, H2O. And you know, because you've probably taken Lewis diagrams at this point, that when we start to assign electrons in the water molecule, we find that there are two non-bonded pairs on the oxygen within the water molecule. You also know that the bonds within water are polar. So we typically show that with a delta plus at the hydrogen and a delta minus near the oxygen. Sometimes this bond in here is shown as being polar using an arrow. Another way that it's shown is we'll put a plus sign on it, and I'll show you what I mean. So let's redraw that bond. I'm going to enlarge it a bit. And if it's positive towards the hydrogen and it's negative towards the oxygen, sometimes what we do is we just put this kind of plus sign in there. And we show the plus closer to the hydrogen than it is to the oxygen. Well, there's another way to do that too. And I said we can do it with an arrow. So let's show that bond again. And sometimes we show the electron density as being closer to the oxygen. And we show this arrow because in a sense the oxygen pulls the electrons towards itself. Its electronegativity is higher than it is for the hydrogen. So if you were to look at the electron density at any given time within this molecule, most of the time the electrons within the OH bond would be closer to the oxygen atom than they would be to the hydrogen atom. Well, why is all this important? It's important because in an acid-base reaction in water, what's happening is the water is actually acting as the base. It is a proton acceptor. Well, where's this proton coming from? Well, in the hydrochloric acid, or HCl molecule, which typically doesn't really exist in water, it's just too reactive, but for clarity, we're going to show it this way. Within this hydrogen and chlorine bond, there are two electrons. So there's an electron and an electron. So here's two electrons in here. Now, chlorine is more electronegative than hydrogen. And in fact, chlorine is one of the most electronegative elements. So this is delta minus. And this is delta plus. So most of the time, the electrons are around the chlorine atom and not near the hydrogen. And in fact, this bond is so polar that it's pretty much ionic in the sense that Cl is actually Cl minus and H is H plus. So this is where the proton donor comes in. HCl is a proton donor because this is an H plus coupled with a Cl minus. You might better think of it as an ion pair. Finish that to a plus and a Cl minus. And if you looked at the Lewis diagram for chlorine, you'd see that a Cl minus actually has a full octet. It has all of the electrons around it. On the H plus, well, hydrogen atoms, if you look at them on the periodic table, atomic number of 1, only have one electron. So if that one electron that usually is on the hydrogen is taken away to form the ion, well, it's actually one of these electrons over here on the chlorine. The chlorine has stolen it. It's taken it away. So let's just scribble that out for now and go back to our reaction. In our reaction, I said that water is the electron or the proton acceptor, and hydrogen chloride or hydrochloric acid is the proton donor. Well, how can we envision this reaction? Well, one of the best ways to envision it is through electron transfer or electron movement, electron shift. And in organic chemistry and general chemistry too, but more so in organic chemistry, we'll show electrons moving from an area of high electron density to an area of low electron density. And I've already said that the density of electrons is high around this oxygen on water. So this is a high electron density area. And I've already said that the density of electrons around the hydrogen is super, super low. Pretty much it's just an H+. So the electrons want to move from high electron density to low electron density. Think of it like opposites attract. Now, when this happens, I told you that really it's this kind of an ionic situation where you've got H plus and Cl minus, but let's pretend that there's a bond here. What would that do? As these electrons come into this area of low electron density, this H plus, any electrons that are involved in bonding here, what are they going to do when two more electrons come in? Oh, by the way, this arrow with a double head like this, like a typical arrow, like an arrow fired from a bow, this represents the movement of two electrons. This is in contrast with an arrow that looks like this. This represents the movement of one electron. It's not a double-headed arrow, it's a single-headed arrow. So this is two electrons moving towards this hydrogen. Well, negatives repel. So these electrons are negative in charge, and there are negative electrons within this hydrogen and chlorine bond in HCl. What are they going to do? Well, those electrons are going to shift towards the chlorine atom. And we show the movement of the electrons again with the double-headed arrow. And this will produce our products. So what are the products? Cut. The products in this reaction are the protonated water molecule, so now the water molecule has picked up a proton, and I'm going to show a bond to the new hydrogen proton. And remember, in that reaction, two of the electrons that were on the oxygen moved towards the hydrogen to form that bond. Now the bond between the hydrogen and the chlorine atom, it disappeared. Those electrons shifted to the chlorine. So what do we get for chlorine? Well, the chlorine is now with its octet of electrons. And it has a negative charge. The protonated water molecule, also called the hydronium ion, this hydronium ion has a positive charge. The chloride ion has a negative charge. Now, if you went back and you looked at the overall reaction, we started with water, which was neutral. And we started with HCl, which was neutral. That is, they didn't have charges on them. They had polarity, but they didn't have charges. The left-hand side of the equation, H2O plus HCl, leads to the products, hydronium ion plus chloride ion. The hydronium ion plus 1, chloride ion minus 1. Total charge, when you add those together, 0. You'll notice that the chemical equation is balanced for charge from left to right. That is, neutral on the left in total, neutral on the right in total. And that's the way it should be.